Hi, we are Team 43, and this is our presentation for the Mars Cargo Mobility System Design Project. For this project, Team 43 was tasked with creating a small-scale prototype of a Mars cargo rover, which will be abbreviated as MACRO throughout this presentation. The materials that were given to the team to design and build this prototype were various LEGO pieces, NXT motors, and Grove Pi sensors. These sensors included an ultrasonic sensor to measure distance, a Hall sensor to measure magnetic field, two line finders to detect black or white on a surface, and an IMU, which would measure acceleration, angular velocity, and magnetic field along 3 different axes. The macro was programmed using Python via a Raspberry Pi, which interacted with a BrickPi and Grove Pi to help the rover function properly. The function of this macro prototype was to autonomously carry various pieces of cargo to designated drop-off zones, all while navigating through different obstacles and paths. Because of this, the macro prototype was given certain standards that it would have to meet to be considered successful. These standards included precise navigation, the ability to traverse various obstacles in difficult terrain, and the ability to safely deliver cargo to the proper site in a timely manner.
Our customer needs were that our robot must follow the path well, complete the course in a timely manner, carry the cargo well, stop in the proper zone, and run smoothly. In this table, we have also outlined the technical needs, technical requirements, and target values of our design. Our technical requirement for following the path well was that it followed the line with less than 2.5 centimeters of error. We also required that our macro would complete the course in less than 10 minutes. The cargo would fall out of our macro less than 5% of the time, and there would be no errors in the program. Our technical requirement for the robot to stop in the proper zone was that the robot would stop less than 15.2 centimeters from the drop-off zone. Here, I have a functional block diagram that covers the major subcomponents of our design. Through sensor input and user input, our robot must follow a path, unload cargo, have proper speed and acceleration, and stop in correct areas. We also use these subcomponents that are included in our functional block diagram to create a work breakdown structure. The work breakdown structure specified the steps that we needed to take in order to include each subcomponent in our design. Our project timeline was outlined in this Gantt chart. We first built the robot and assembled the cargo container. We then programmed each of the sensors, attached the sensors to our rover based on the constraints of the code. Throughout the project, we made sure that we were documenting our process. Each member of our team also had separate roles. Grant was the main coder and builder. Sarah and I, Fatima, were the main recorders of the process. Evan had the role of building the robot and encouraging the team. Each of us took turns timekeeping and being the devil's advocate.
In building the macro, we had to make 3 major decisions when brainstorming different options for the design of the vehicle. We thought that it would be most beneficial to make decisions based on the results of decision matrices. We were unable to come up with data for these decision matrices without building the actual macro, so we made estimations for the values of the technical needs. Our 3 major decisions were the type of vehicle, type of unloading method, and the motor and wheel setup. Our first decision was the type of vehicle to carry the cargo. Our options were a pickup truck, where the cargo sits on the back of the macro and has 4 walls keeping the cargo secure like a real pickup truck. Second, we had the dump truck idea, which is similar to the pickup truck but sets up the cargo differently for offloading. Then we have the crane idea, where there is a Lego pole sticking up from the center of the macro and the cargo hangs from a string attached to the pole in the air in a box securing the cargo. Next, the forklift idea, where the cargo is carried in front of the macro on a flat surface. And finally, the skid loader, which is similar to the forklift, but the cargo is carried in the front in a basket-like structure. Our final results of the decision matrix conclude that the pickup truck was the best option for the project. It performed well with all of the customer needs that our team deemed important, especially excelling in reliability. The dump truck performed as the second top choice. However, its setbacks were that it was more difficult to build and required too many resources. Third place was the forklift. Its setbacks were that it performed negatively in delivering the cargo in a timely fashion and was not deemed to be reliable. Fourth was the skid holder, which did poorly in delivering the cargo safely and used too many resources. And last place was the crane, which did poorly in every category. It was not reliable, used too many resources, did not deliver the cargo in a timely fashion, and it was the hardest to construct. We created decision matrices for each decision, but for the sake of time, we will only show the results for the next two matrices. For the unloading method options, we came up with a conveyor belt option in which the cargo moves with a belt on top of the back end of the macro. There is also the push-off method, where the cargo is pushed off of the rover onto a ramp by a platform attached to a motor. And lastly, there's the dump truck option, where the floor of the cargo, where the floor that the cargo rests on is lifted up by a motor, having the cargo slide off due to gravity. Our final results of the unloading method decision matrix conclude that the push-off method is the best option for the project, having the greatest reliability, something that our team deemed as an important qualification. Next, the dump truck came in a close second, but was harder to code and would require more time to unload the cargo. And lastly, the conveyor belt required more materials and was significantly larger than the other methods. Lastly, we made a decision matrix for the motor and wheel setup. According to the results, the best option was the two-motor, four-wheel option with one wheel per motor. We thought that it would do the best. However, after actually testing the macro, we decided to get rid of the front two wheels because it was too hard to turn and the turn radius was too large. Second place was the three wheels, two motor option, having two wheels in the back attached to a motor per wheel and one wheel in the front of the macro. We did not choose this design because it was significantly harder to construct and would be too slow when turning. A close third place was the two motor four wheels with two wheels per motor. However, it performed negatively in speed. And lastly, the four motors, four wheels, one motor per wheel proved to be the worst option with too many materials necessary and being the hardest to construct.
There are 4 different sections of code that made up the software of the macro. We used the ultrasonic sensor to detect if there was an obstacle in front of our robot. If the ultrasonic sensor detected something in front of it, both the motors turned off. We used 2 line finders to follow the path. If both sensors read black, the motors for the wheels moved at full speed. If the left line finder read white and the right line finder read black, the rover turned right. If the left line finder read black and the right line finder read white, then the rover turned left. The rover turned by keeping one motor turning forward and the other motor turning backward. We used 2 motors to unload our cargo. One motor was used to push the cargo and the other motor was used to lower the ramp in the back. For our code, first, the motors attached to the wheels stopped moving. Next, the back motor was turned to lower the ramp. The pushing motor was then turned to push the cargo off of the platform. Finally, the cargo unloading motors were returned to their original positions and the motors attached to the wheels began to turn. We used a Hall sensor to detect magnets and allow the robot to locate drop-off zones. We used a counter in the code to keep track of the different drop-off zones. At a certain distance from the magnet, the cargo unloading code would be used to unload the cargo.
For the final design of the macro, we made some adjustments from the initial design. We added an undercarriage to hold the Hall sensor. We removed the 2 front wheels to decrease turning radius and allow the Hall sensor to get as close as possible to the ground. We raised the rear supports so that it would not lift the wheels off the ground on slopes. We filled in the truck bed with spare pieces to help cargo unloading. We moved the line sensors further apart to help line finding code. And finally, we increased the length of the unloading ramp to decrease the angle the ramp made with the ground.
To test the success of our macro's final design relative to the technical requirements mentioned earlier in the presentation, we conducted a number of tests which gave us quantitative data. One of these tests was to track how accurately the macro was able to follow a line. We conducted 10 trials, and for each trial, we measured the distance from the center of the robot to the edge of the nearest black line. The results of these trials are depicted on the graph shown here. We found that the average distance from the line was 3.1 centimeters, which was slightly higher than our technical requirement of 2.5 centimeters. Another test that we conducted to ensure that the macro would function properly was to measure the average distance from a designated drop-off zone for each cargo piece. We conducted 10 trials for each piece of cargo and averaged the distances of these trials. These averages are shown on the graph here. We found that the average distance for the cylinder was 9.1 centimeters, while the average distance for the cube was 12.1 centimeters, and the average distance for the cone was 14.6 centimeters. This equated in an overall average distance of 11.9 centimeters, which was within our set technical requirement. During these tests, we found that the drop-off success rate was around 80%, meaning that the cargo was unloaded in the correct orientation nearly 80% of the time.
Based off of initial data, we were confident about the robot's capabilities. However, the macro was unable to complete the entirety of the course. The line finder code did not work correctly, and neither did the code for the magnetic beacons. It could not get over the hill and veered off course during the speed test. It did, however, get over the small obstacle.
From our tests and demonstration results, we were able to identify many major pros and cons of our design. One of the major strengths of our robot was its cargo carrying and unloading ability. Although we were never able to test it during the demonstration due to issues with the magnet detection, the earlier test shows that our cargo unloading had the potential to be very successful. On top of this, we never had the cargo fall out of the macro when traversing the course during the demonstration or during any of our tests, meaning that the cargo carrying area was very secure. This was only reinforced by the fact that our macro had a very sturdy structure and chassis where nothing broke off or fell, meaning that there was no physical malfunctions with the macro. On top of these structural components, the code and programming was very organized, which allowed us to easily edit and eliminate any errors we encountered, which was especially useful during the demonstration when fine-tuning changes had to be made. For cons, we felt that obvious shortcomings were the line following ability and the magnetic detection, both of which malfunctioned horribly during the demonstration. We also believe that the lack of ability of the macro to handle obstacles was a major drawback, as it essentially meant that the macro could not handle the hill or any serious obstacle that was put in its way due to its motor and sensor setup. These issues were only compounded by the fact that our macro was rather large, which in hindsight was not a good idea. The extra size meant that it was much heavier and bulkier, and which resulted in a higher power need to make it over more obstacles that much smaller macros could traverse much more easily.
After looking at the results of our testing, there are multiple areas where the robot could be improved. Due to the way that offloading motor was rotated, a large part of the force imparted was in the vertical direction, so the cargo would get pushed down and get stuck on some of the holes in the cargo hold and then fall over. We'd fix this by redesigning the pushing motor so that the force was purely horizontal and filling in the rest of the cargo hold so it is completely smooth. The line finding code caused the most issues during testing. It was not designed for all scenarios, and it could easily malfunction if the line was a different color or thickness. Additionally, there was no way for the robot to self-correct if it was completely removed from the line. This would be improved by rewriting the code to allow for all thicknesses to be valid and the addition of a color sensor to account for lighter lines. The initial design included 4 wheels, but the front two were removed to account for the undercarriage that contained the Hall sensor and to improve turning radius. This meant that the robot was unable to get up large slopes. In retrospect, we would re-include the front 2 wheels and hook them up to the 2 motors for front-wheel drive. The robot was also very large and heavy, leading to several problems with parts bending. To improve this, we would redesign the robot to be more compact, including reducing the size of the offloading equipment and removing excess pieces that contribute marginally to the stability. Thank you.